Um, I think we can start more or less. I will appreciate if for the first moment you will all turn on your cameras because I can see you. After this, I think it's possible to turn it off. But for a moment, I would glad to see my class. Maybe I will remember something. Probably. Okay. It's not obligatory, so if you think that it's impossible for you to turn it off, turn it on, just don't do it. Okay. I think we're here. I'm glad to have you here. Okay. And I hope that most of you are here, so we can start. First, I would like to introduce myself. I'm George Morose, but everybody will call me Garrick, so I'm used to it. I think we also have Ina here, but she's a little bit ill. That's why we can't see or hear her. But Ina Zibir is also here, so uh, we will alter our classes. So sometimes it will be me, or sometimes it will be Ina. All the time, all classes will be more or less of the same structure. So we'll have something like classes, usual classes, like when I will boringly try to go through some theoretical stuff, and afterwards we'll have some kind of seminar, let's say, where we'll try to apply this to something or to real data. We'll use mostly prot and some R scripts. And probably this year we'll change a little bit in order to have the package that I've wrote for phonetics used in class. So maybe it will be a bit different from other classes. Okay, the first thing I want to ask you, have you read this chapter that I've sent you? Most of you know it. So it looks like you do. So do you like to have it? Do you have an ability to turn your audio on? I think you can. Yes.
Yes.
Okay, cool. And the one thing that I need to say that all classes will be recorded. So afterwards, I will put link on YouTube link to on the page, so you could look it afterwards if you need. Okay. So everything is recorded, and just know I need to remind it to you. Okay. So first thing, I wanted you to read this chapter, and I think this is weird to think to do at the beginning, but I would like to have you a small. I think that I will send you a small Google form in the chat, so it's here. It would be nice if you go through it. You have the first answers. 1, 2, great job. I think it's time to stop this. So finish in a minute. Okay. Okay, let's stop here. So last two-person, please submit your answers, and we will proceed with the lecture. Um, Answering some private messages, yes, it will be recorded, and it's now recording. So you see this message on the top is live on YouTube. So it will be there, and I will link it to the page. Here is our page with all materials. I will try to store it there. And probably I will share screen now. Okay. Close. So this is the page that we'll use. So I will update it before each lecture. And as you see, we'll have first lecture. So we can download it and use it. So it's PDF file. There is also something that's called final mark. This is from ages when we treated our course as a separate one, not as a part of the theory. How do you call it? So whenever the course is called, it's part of some major course, and our part will be based on homeworks and exam. And here is the scaling for both of them. So see here you have weights for the homework and exam. So you see it's possible to do only homework. It's possible to do only exam, or you can do both. Okay, I think that it will be 10 lectures plus seminars. So it's something like 10 days, during which we'll cover different topics on instrumental phonetics, and mostly we'll work on this. So what to do with the instrumental survey, and how do you do this, and so on and so on. First lecture is a little bit connected to physics, because it's a little bit boring, and it's not so mm, it's not insightful for the phonetic research itself, but it's important to have this basement for all of you. So we decided to have it here. Okay, and I think that I will just download it and start. So here it is. Oh, this is the old link, or I didn't update it. It's a pity. But anyhow, I think I have a newer version. Since it's differ only in date and link, so it doesn't matter much. So, but I would like to use the newest one. Okay, it should be here. Okay, yeah. It it will be the same. The difference only you can see here and here. So this link to the, I think this is linked to the correct page with the same PDF, but we'll see. Okay. So what do we have here? First, course website. I think this is the wrong link. Then our expectations. So we expect that you've read this chapter that I've sent, and you are able to use IPA symbols. And this is more or less, it's not so useful, but it will help. We also, during the course, we expect some basic R skills. So something like import CSV file to R, using dplyr R and ggplot2 will be important, I think in 3 or 4 weeks. But I expect that you have our classes now, aren't you?
Yes, we're having them.
And how many classes do you had?
We've had 2 so far.
Okay. And this is with Ilya Shurov, isn't it?
Yes, and also Vanya Poznikov.
Okay, cool. Okay, cool. So this will be something that we will need for our classes, but it's not something like all scripts, all R scripts will be provided. So don't be afraid if you are feel a bit shaky with R and new programming language and so on and so on. The most, I think, work will be done not via R. And from here, I think I think it's nice to talk about phonetics and phonology itself. How do you see it and how do you feel? Because you actually read some basics of articulatory phonology and phonetics, but I think that I wanted to have some details here. So mostly you have this division between phonetics and phonology, and phonetics is treated like some subfield. Sometimes in some theories it's treated as some just realization and physical part of some phonological interface of language. And this is complicated talk at all, but the main idea, if you're not familiar with phonology and phonetics itself, will be that the simple idea will be that just phonology working with some language units, and phonetics is just realization of those units. So for instance, we need to model something like, I don't know, so we have something that we call phoneme T, and we need to model how do we pronounce this T in different positions. So uh, when we have it in the beginning of the word, it's realized as toy, for instance, in word toy. It's T, aspirated T. In middle position, it actually depends on your dialect. So, for instance, um, if you have American version, it will be better, for instance, in the word better. In British version, it will be better, better. Oh, I need to better, something like this. Uh, and more or less the same will be in, I don't know, Cockney dialect, it will be better, and so on. And when we have it in the end, or after the some fricative realization will be also different. So for instance, we'll treat all those units as the same, but for instance, when we have word um, stop or storm, the idea that when we have those words, T, they're realized not as aspirated but unaspirated. I'm not sure that all this true from my different and weird English pronunciation, but uh, I think it's something that you can call. So we have one unit, and this is different realization in different position. Uh, and the spread of different realization is due to some phonological rules. And afterwards, after this, it could be modeled as some random process uh, when you deal with some acoustic features of the realization, and you can uh, it will be different for different people, different, for instance, female or other groups of people. So for instance, students and teachers will be talking in a different way. I don't know, female and male speakers will talk in a different way, and New Yorkers and Londoner will be talking in a different way. And those features, some of them connected to their phonology, but some of them pure phonetics. So, for instance, I don't know, realization of uh, a sound will be different. So, as you see in this picture here, when we have phonology on the right side and everything is schematic and just like we model, and we have this that sound that we have there that represented with these D graph of an A and E. So this sound could be really different, realized in different way in different English varieties. So you can have something like, so something simple word like map, uh, so something that you can have it on the wall, could be realized differently in different languages or different varieties of the same language. So you can see, you can have map, you can have uh, more like a realization, you can have more like a realization, you can have weird New Zealanders pronunciation when it became ia, so it will be miep or something like this. I think this is the something that familiar with them. So this kind of rules of phonology, but what extent of these changes sometimes could be phonological and phonetics, and this could be question to phonology. After this, so we have this. So we decided to isolate one group of people and say, let's say we talking with I don't know, some weird uh, small village in Britain, somewhere in Britain. So we have it there, and we talk with, I don't know, collect some speech samples from different people. So we expect that, for instance, vowel chart, when we plot it using F first and second format, will be more or less the same. So the system itself will be more or less the same. But we don't expect that every value of f1 and f2, so first and the second format, will be the same. But we expect a little bit variance in this side. The same will be with the not with the color of vowels, all these difference like a, but also it's possible with duration or aspiration or speech rate or everything. Everything is a random process when some people have preferences to, I don't know, faster speech or slower speech, but there are also some situational cases that will drive those things. But mostly they have some, let's say, equilibrium, and they deviate from this equilibrium in one or another uh, direction. So, for instance, imagine that we collected, uh, I don't know, 1,000 of realization of word yes, and then we measure the duration of this word. Again, even from the one person, it will be more or less random. The duration will be have some equilibrium centrum, but random split aside. And I think mostly phonetics treat it as such a measure. So you have this study of some units of pieces of languages that are separated from it, and then we interested in acoustic features of those units. And those acoustic features could be different. So it could be duration itself, but it's also possible I don't know, also lack of sound could be informative. So for instance, I don't know, probably in Italian they have this difference like t and two, one t and two t, and well there will be, maybe Ina remembers something of this. I don't know. I think no, I can't remember. I can't remember, but anyhow, the duration of silence also could be informative. So, for instance, when you have two syllables like ata and atta, this also like important information. But also there are some acoustic features like what you can see on the sound spectrum, and this is something that could be analyzed, and this something that we will work with. Um, this course is about acoustic phonetics, but we won't get into any details about phonological theories and the ideas. Uh, but remember that they are a little bit different studies actually of itself, but they are more or less connected. So it's impossible to go somewhere, for instance, to the unknown village of the Caucasus when nobody ever been. So you got there and bam, you want to research some phonetics, and then you research, and then so it's impossible to have something like this. So study like this. Why do you think it's impossible? Maybe I will do even this. Why do you think? So the question again, because maybe I talk too much. The question: imagine that we got to the unknown village. We don't know the language itself, or maybe we know. For instance, let's say we know something about this language, but uh, why uh, why I'm claiming that it is impossible to do phonetic research itself separated from phonological part. Or maybe we can. Maybe you think that it's not sufficient at all. So we can go anywhere, take a toolkit, analyze everything, done. Phonetics is done here.
Well, maybe because different phonemes can be realized differently, and we need to know some like important features of the sounds. Like that's why we need to know some phonology. Or maybe it also depends on what kind of study you want to conduct. I don't know. Like
Oh,
what kind of phonetic study you want to conduct.
this is a nice point. Is it possible to come everywhere and research speech rate? What do you think? Do you need any phonology for a speech rate?
Probably not.
Yes, it appears so, but it's not true. And here is an example. When you study speech rate, you need something like measurement. So you have something like rate of something, but those units should be, it could be segments. This is weird solution, but it could be. It could be syllables. I think this is the most common solution. So how many syllables per second this person produce, and so on. So sounds fine so far. You don't need to know anything about language in order to split something into the syllables, but he had some problems. For instance, when you have what kind of examples? And English examples here are a little bit weird, actually. But anyhow, uh, for instance, we have word apple. Common word. How many syllables is there?
Two.
Two?
One?
One? Who knows? Three will be any option?
But it depends how many schwas do we count, if we, and perhaps how we pronounce it. If we pronounce it like apple, it's perhaps one, and if we pronounce it like apple, it is two. But maybe there is a schwa in any case in the second after p. So if there is a schwa like in any case, so it is always two.
Yeah, this is exactly the problem that I wanted to have, because it's really hard to pronounce something like pl without any intrinsic having something like, and so it looks like there is a schwa there, but it's impossible to really. So you can look at the spectrum, and then it will be different. For instance, when you have apple or apple, it could be not like two two-way distinction. It could be a scale when you have smaller schwa and longer schwa, and you need to decide whether it's something like whether it's a unit. And you can ask people, but they will say you some bullshit. So this is not really important. But I think Apple problem is the actual problem. In Russian, we have more or less the same. Um, we have wind, like theater, or theater. Theater. In Russian, I think it's theater, and it could be pronounced with schwa, theater, or without it. And there is some Pushkin's lines that have it there, and it's clear that's in there it's supposed to read like theater without any schwa. And there is also a case of variability. It's possible that, for instance, some English speakers will say apple and some will apple without any schwa. So all those matters are important because you can say the contents of this word, even for such a stupid measure like a speech rate, is actually more or less simple to do, but you have this problem. And also the problem will be how precise would you want to be. So for instance, Um, for instance, when I say I don't know in English, we have this I don't, but it pronounced like don't. Uh, and probably everybody will, I will convince everybody that it's one syllable. Sometimes if you ask some English speakers, probably they say that too because it's do not. It could be, but sometimes something like this. But we know, we analyze what we have, aren't we? So we collect some text and we need to check whether speaker pronounced do not or don't. But it's also possible uh, to reduce this to something else. And sometimes in some English realization, it will be omitted, even if I don't know, will be uh, merged into I don't know. And then we have this, some new form. How do we count it? So is it, when I have I know instead of I don't know, is it accounted as a one syllable or two? Because it's actually I don't know, or it's ain't as a one. So this solution will be all the time. So you need to have this solution all the time, and it's important. It's impossible to do without phonological knowledge of this variety that you work with. Mm, and this is for the simple rate speech. If we want to measure vowels, oh, it will be disaster without knowing, I don't know, having some dictionary. What kind of vowels are present in this variety? So imagine that I send you, for instance, into to New Zealand or Australia, and with the one simple task, go to this village and record vowels, and then create a beautiful plot with the some one even with one speaker, it will be disaster because you don't know how many vowels in English. And even if you know how many vowels in English, you don't know how many vowels in the in Australian variety of this English. Uh, and even if you know how many vowels in this Australian variety of English, you don't know what's going on in this particular village. You know, it's it will be complicated all the time. So you need to compile some dictionary and check whether they have this vowel and what do they have in the place of what we expect to, for instance, what do they have for map, app, a sound? What do they have? What do they have when we have, I don't know, this is story about sheep? What do they really have this E sound there that is different from ship? Uh, Sometimes they do, but sometimes it will be disaster because they all changes and all over the world. And this English varieties are really beautiful story about them. Is that all, all of them a little bit changed the vowel and it became a little bit different. So also all those things, it's possible to go there and do the research, but it will be a little bit complicated without this phonological knowledge. What kind of units do we have? And this is important for phonetics, I think. So the only one thing that phonetics needs from phonology are units. What kind of units do we have in this language? What kind of units? Uh, you can also even uh, uh, put this question in different way. What kind of units uh, do we all researchers assume there are in this variety? Because it's also possible to do this way, because um, it's possible that we are coming to some variety, we don't know much about it, so we have our assumption and then we'll check it. But in order to prove that this, so for instance, imagine that we came to Australian village with weird sounds, we collected our data, and for our ear, I have a feeling that the sound is different. So, for instance, they have, I don't know, they have a sound like in map, and they have, I don't know, e sound like in sheep. And imagine that for my ear, I have some feeling that they merged together. How do I prove it? Hannah, maybe I ask you, please.
I didn't hear the question. How do you prove what?
So imagine that I have a feeling that E vowel in our variety that we research and A vowel, like in map, are merged together. How can I prove it? Because so I go to this village and ask, how do you say map? And they, meep. How do you say sheep? And they say, sheep. And I say, wow, this is the same. Wow, cool. I want to write an article on it. So what do you suggest?
But you try to find minimal pairs, like you said just now, like map and sheep. So there is no like I don't know, map and meep. I don't know if there is a word like meep in English, but imagine that there isn't. So if map and meep are pronounced in the same way, so there is no minimal pair. And I don't know, they confuse these two words, and therefore you can claim that R and E are merged in this variety.
Yeah, that's exactly what I wanted. Because the problem will be, so imagine that I don't know about the word meep itself, but I think we all know the word meat. And imagine that I have that they pronounce meep the same way as meat, and but the problem that I wanted to point out that it's impossible working only on these varieties and reducing and vanishing all our knowledge about other Englishes from our head. It's impossible to get this. It's could be a finding only when you compare this to other languages. Saying precisely phonology of other languages. So you know that in phonology of some other varieties of English, there is a distinction between E and A, and they lack this. So you collect, so in order to prove it, you need to collect those words that in other variety of English are distinguished. And then you show that they have more or less the same vowel space and they overlap. And then you have it proven. But this data should be taken from phonology, and from phonology even not of that variety that you are working on, but of that variety that you are not working on, so that is known from literature. So that's where you have phonology and phonetics interaction. You need, for phonetics, the only thing you need is give me units that I will work with. And then it could be reduced to something like, and then I will say what is the difference between them, between those units. Okay, is it clear? Maybe you have disagreement or some other examples. I would be happy to hear it.
I have a question. So when you say when we come to a village with an unknown language, so you mean that we do not know what language family to which language family this language belongs, and we don't know like anything about this language. So if we do not know the language family, we do not know with which other languages we can compare this unknown language. So you mean something like this, yes?
I think general answer will be yes, but I think that I will elaborate it a little bit because I started from this perspective that we have phonology and phonetics, and I asked you, is it possible to have pure phonetic research without any interaction with phonology? And since nobody answered, we elaborated this situation about this Australian village. But the problem is that it's impossible to have universal phonetic research without just come to one language and I don't care about another language, I will study it, and so on and so on. You need to know something about the language that you're working on. That's why there is no any pure phonetic research. You need those phonological units in your phonetic research. That was my example with the unknown language, and that so you don't know anything about this language, unrelated, don't know anything. It's hard to have phonetic research there because you need a phonological study before. So uh, you can collect some dictionary from the speakers, but then you will need to split it to the some chunks, and this will be already a phonological work. So because they have, for instance, back and big, and you already and there are two words, and you need to all the time you need to decide whether there are whether those are the same sounds or different. So if you come to some unknown language and you don't know much about it, and you start working on it, you will need this phonological background all the time. But that doesn't mean that you will need this phonological background in terms like phonological theories. Like it's not like you need to know optimality theory in order to do phonetics. No. The idea that you need to have some phonological interpretation of this language before you start phonetics. Okay.
So you mean, for example, if some foreigner studies Russian language and he encounters a word balagan. So we, as I remember or as I understand, in this word we say that um, there is stressed balagan, the last syllable. The first is schwa, and I forgot how this phoneme is called, but it is not the same R that is under the stress. So if a foreigner studies this word, he would, and if we study this, we say that all R's are the same because we know the structure, or we also say that those three are different.
So we have this.
Did you understand me, or I?
So we have this something like this. Maybe I'm not good in writing this. Maybe it's a bad idea. Maybe I want to do it like where. Okay, let's have it here. So, for instance, imagine that we hear something like oh, why it's not. Wow, this is strange. Okay, maybe it doesn't work to work with you. So I have something like this. And your question is, if we know something about, so we need to know to have something like model in order to do it like this. Is this your question? So how we know from this form that this is true?
Yes, perhaps.
And I think this is a question to phonological theory, because it's we do have this form, and we can create some theory that will treat it like this, or like this. I think it's impossible to prove that it's there, isn't it?
Yes, yes.
It will be hard. So it's possible to have theory that will claim something like this. It's also possible to have a theory that will actually don't care about this, and it will have something like, oh, and I don't know how to do it, but it probably could be done like this. No, not good solution. But imagine that I wrote A and O as one unit here. So they don't care about whether it's A and or, but it's something that became schwa. It's also possible to model, actually, it's possible to model it like this. It's strange to have this, but it's possible, I think. I ignore these syllables, but it's also not so clear. But I think we also need to put something like this here. Yeah. And those are different phonological theories that you need to have before you start your phonetic research. You need to have some, I think it's possible to have something like ideas why one theory is better than another, but in most cases, it's I'm not sure that all the time you will have all answers. So yeah, but I think this is a problem of creating a phonological theory. I'm not a big fan of all those, but anyhow.
So without a theory, we cannot also analyze in a known language.
Yes, without theory about those languages, but sorry, without theory of this of the structure of the phonology of this language, it's hard to make a phonetic research. The problem is that you don't need a really strict and non-controversial theory. So it's possible to have shitty theory, but you can start with the phonology. Oh, sorry, you can start with phonetics. So if I have a list of words and here I have something like this, then I create some idea that, for instance, let's treat it like this, and then go on, proceed with other words. Afterwards, we will correct it or not. It will be the problem here. This is another actually question. So since you have, so sometimes phonetics used in order to prove something in phonology, weird cases, but sometimes it's happened. So for instance, imagine that you that we proved that we came to the Australian village and there a merged with e, so they have meep and meat. So after this, we proved that they are merged vowels. After this, it's possible to say something like, they don't have this unit, a, so they have less vowels. And that means everything that we maybe recorded using this sound should be changed. So it will be circular. So you change phonology, change phonetics, and phonetic study, and maybe it will influence some phonetic studies and so on and so on. So there is no any finishing point when you say, I know everything about Russian phonetics, for instance. There is no any way to say this. I know everything about Russian phonology. I think it's also could be problematic too.
Could I ask,
Sure.
do we need minimal pairs for analyzing balagan too?
I'm not sure. This is actually something like intrinsic phonological problem, because at the beginning of phonology, this is weird that we started to talk about phonology, but anyhow. So at the beginning of the phonological theory, minimal pairs was everything. So if you have minimal pair, then you have a proof that it's something. If you don't, there are actually some tricks about to get there. So for instance, if you use only minimal pairs, there is no any minimal pair for huh aspiration, like in words hat. So this fricative hat at the beginning and hang at the end. So nasal ng. So it's since they are positionally distributed, like one at the beginning of the syllable and one in the end of the syllable, it's impossible to actually have a minimal pair for them. So it doesn't mean that they are phonemes. And even Trubetskoy agreed with this. So those kind of things, okay, could be, but no, you don't need minimal pair for everything. So this will be a shortest answer. And then after this, phonological theory actually evolved a little bit out of those searching minimal pairs for everything will be a pain. And for some sounds, it's impossible to find minimal pairs. So it's nice to have them because then you can easily prove that something is like phoneme-like behavior, but you don't need for this minimal pair distinction for everything, I would say.
And how then we will prove something when we have a word which do not have a minimal pair, like with hat and something else? There is no strong proof, then
Yes, proof. For whom do you need proof?
for scientists.
Yeah, that's what I said. In order to do phonetics, you need some phonological theory, but I said that this phonological theory could be shitty. So it could be that, for instance, you don't have any all proofs that you need. Maybe some part of your theory is bullshit, but you can do phonetics after this. So the idea, yeah, phonological work is hard work, but you don't need to wait until all phonologists finish their work and start to do phonetics, because in most cases, for instance, in Russia, when you have a field worker, in most cases, these guys who do phonology also do phonetics, so it's the same person. Even if they are distinguished somehow, it happens. Then they interact with each other and talk a lot. But again, you don't need to have a final state something. You can have something shape. So how many vowels do we have? 5 or 4? I can say something. If somebody will say we have 5 or 4 vowels, I can start phonetics from there. You follow from your face. I have a feeling that you're not convinced, but maybe this teacher's abilities to read the students' faces that come up in the isolation, and that we all teachers are really want to see students' faces. But I think this is overrated, and maybe teachers are not so good in reading students' faces.
It's not like I'm not convinced. It's like I'm still now thinking about how we can prove something, because it's impossible for me, as I understood, to say just I hear a different sound here. That's why it's different.
This is all the time will be half proof. Because it's really strange thing. I've never thought about this much, but what I would say to you now is that anything. So I think this is a philosophical problem of that called hermeneutics, I think. So imagine that I have some source about something, and in order to fully understand this source, I need to understand references from this source. And then in order to understand references that I'm reading, I need to understand the reference of these references, and so on and so on. And there are turtles all around, all down there. So it's impossible to read everything. So when you prove something, you are actually doing something like this. If you think that this is true, then I can make this claim. And somebody in the future could ask, your first claim is a little bit shaky. It's not like this, but it's actually like this. And then you will need to say something. Like as we change this, this is changing like this, not much. Okay, still true. And so on and so on. So answering your question, Ksenia, will be there is no any final point when you say, I'm done. Everything about this matter is known to the universe. Just read this and this book. It will be research all the time because it's in order to, when you make something better, it will also make it possible to create a new work based on your work, and so on and so on. So, and sometimes it could be not controversial when you put it, but after some tones of other works that stay upon it, it can become controversial, and then you will need to change it.
So, and about Balagan, so is it true that it's like this problem is like not impossible to solve, or
this is I think this is another thing. This is for some reason became a philosophical lecture from acoustic lecture, but anyhow, we can deal with it. This is another thing because in science you can have different tasks. Some of tasks are pure, I'm interested in what do we have here. And when you model this, you just want to model some behavior. So answering your Balagan question will be, I think it's possible to have multiple models depending on what do you want to model. Because if you want to model reduction, you actually don't care, or even vowel quality, you don't care about what kind of vowel is there. So it could be, and then you can bring all kind of theories that you have. So it's possible to have this, it actually comes to something called Moscow Phonological School but I can remember this. So somewhere there will be an archiphoneme, and I think
Hyperphoneme in
this is
Moscow
from
school.
Trubetskoy. In Moscow's, I think in Moscow Linguistic School they have something. They don't have them, I think.
They have hyperphoneme.
They have hyperphoneme. But then in generative phonology, they involved something like, so you need to have this specification of features for all units that you are analyzed. But actually, it could be not fully specified. So there is a whole theory, and even not one theory, but several theories of under specification, so non-specification. So for instance, when you have some units that are not fully specified, and this could be also such a case. And this is a problem because I have multiple models, phonological models that will create a model this behavior for you. The question will be, what kind of task do you have? If you want to have a simple solution, they all will be uncontroversial to each other. If you want to use it somewhere, for instance, for stress assignment, or I don't know, in some neural net that will assign stress to unknown word, that will be another task. So for instance, how do you use this? Uh, you'd rather have this specified for those neural net that will assign stress, because uh, in a neural net will see only orthographic words, so it should be a letter there, and so on and so on. So goal is actually sometimes make task a different task.
Mhm. So I got to the main thing. It's all complicated.
Yeah, I actually don't like this kind of. There are some teachers that actually have this impression that everything is complicated. I don't like, and I've never thought that I could be such a teacher, but here we are.
But it's all about the start.
Yeah, this is okay. Okay, now it's have 27. Wow. So this long phonological, philosophical question. I think then it's nice to have breakdown for 10 minutes. And let's meet in 7:40. Okay? Hello, hello. Type 1 if in the chat if you are here. Oh, a lot of people. Cool. Okay, maybe then I proceed with what I wanted to do during this lecture, and then I think we'll move similar to the next week. So after this, I wanted to tell you more about something that called simple harmonic motion, and going deep into the phonetics grounds, and this mostly physics for now. So each sound is actually some kind of wave, and simple harmonic motion. So there are periodic motions and unperiodic motions. So if motion repeats itself, then it's unbelievable periodic motion. If it's not, then it's unperiodic. And simple harmonic motion is some kind of periodic motion that mm, consists of two things. First, there is some equilibrium position, so it more or less go back to this position, and it's possible to be there. And there is also some force that will restore this object to equilibrium position. So it pushes away and go back. So here is this simple sinusoidal, I think, motion that, I don't know, starts from 0. So on the x-axis you have t, so that means time, and y is just displacement. So you have something like displacement, and 0 is this equilibrium position. This could be not connected to the sound itself, but we'll connect them, I think, in a minute. So first, the most important thing for the simple harmonic motions is amplitude. So this kind of displacement, the maximum of displacement, from the equilibrium position, period. So amplitude you see here in red. So this is, you have peak of your displacement and then compare it to the equilibrium position. You have period, so it's the duration of the time when one cycle repeats itself. So here we have t, and this, I think, will be repeated itself after the same cycle. And there's also a frequency, it's the number of periods or cycles per second. So you have frequency that denoted as f. So here we have formula for this. So frequency is 1 divided by t, when t is the duration of the period. And simple arithmetic, and you can move forward and backwards. So we can move frequency down there, and so multiply everything by t and divide everything by frequency. And then you have another connection. So we can correlate the physical properties of sound waves with our perception. So we perceive changes in frequency as pitch. So if you have something like some melody, so I don't know, and this is different in pitch, that mostly used for, you can find it in intonation in language, or probably in music a lot. And we perceive changes in amplitude as loudness. So something could be said really quietly like this, and something could be said really loudly like this. And this week relates of if we have high frequency, that it means that, so if we have something like one, let's say, motion, so one wave, if it's faster than its higher pitch, and if it's if the amplitude is high, then it's loud. So far, so good. Do you have any questions? Cool. Then I will keep talking then. So the next important part called phase, and this is important for waves itself, and I think it will be important for Fourier transform that we'll discuss, I think, today maybe in a little bit faster way. So phase is something like, imagine that we have one cycle and then we divide it into some specific, so for instance, some specific parts. Most and here, for instance, we have this divided by 360 degrees. Sorry. Since this is used because all sound wave physics, actually this repeatedness in physics connected to the circles. So that's why it a usual task to divide it into the degrees. But it also can be represented with 2 pi's if you are more familiar with radian notation. So if you have two waves, they could be differ in, sorry, if you have two waves, they can be different in phase. So for instance, here you have two waves. They are more or less the same, but they are different in phase. So one is 180 degrees ahead of another. This also could be smaller change. It could be, for instance, 90 degrees and so on and so on. Why is it important? Maybe, why is it important? Because when we will talk about addition of waves, this will influence the result. So it's possible that the same wave could be summed into, if they are in the same phase, the sum of two waves will be twice of the original one. But if they have this 180 phase difference, then the summation will result as 0. We'll see it. All waves could be represented like this. So here we have A as amplitude, cosine 2 pi frequency, time, and here we have phase. This is more or less standard thing for representing waves. Cosine actually could be changed to sine. It doesn't matter much. So it doesn't matter for concrete waves, but for formula, it doesn't matter much. So you could see another formula. But for me, it's important to have that this is a function of t. So you have both there, and then a is some constant. So amplitude. So if you have some example over here, a here equal 1 because the maximum amplitude here equal 1 or minus 1. So that means that a value over here for those will be 1. Okay, so f is a frequency. So if we go back to this wave, I think it's hard to estimate, but it looks like we have more or less 1.5 cycles per 10 seconds. So frequency is not really high here. Okay. Any questions now?
S is just a variable. S of
It's the result. So this will S function of t is the result wave that we see over here.
okay.
Isn't A always positive? At some point you've said amplitude
Oh, this is a nice question.
-1.
Yeah, I would say that it's always positive. Yeah, I think it doesn't matter much, because if it will be negative, the result will be the same, but with the opposite direction. So for this wave, it will be just movement. So it will the result will be like change in phase also, but it shouldn't be all the time the same. But this is a nice question. Thank you. I think I will get in a moment. Sorry, I decided not to sniff all the time. Oh, some more one. Oh, I can type 1 here. I arrived. Okay, let's move on. So we have this representation. I think it's important to know where to find it. I would have never asked you to know it from heart, but it would be nice that you know that it consists of those things, and those things are amplitude, frequency, and phase somewhere. Actually, you can even ignore phase. But we will need it next time when we discuss wave production in prod. Well, actually, we can change it and do it now, but anyhow. No, maybe not. So those those harmonic motions that we've seen before were actually ideal. So they never begin. So it have infinite values to minus infinity, and have infinite values for plus infinity. So it like never ends and never starts. But there are also so-called damped and forced harmonic motions when intensity or amplitude for those waves are not stable, and it's changed through time. So, for instance, here you see a wave with the with the same frequency, so it's half more or less fixed frequency. So frequency is not changed here, but what is changing is amplitude value. And this is called damped harmonic motion. And the opposite case is forced harmonic motion. So when in most cases, you have something like this. So sound begin with forced harmonic motion, and then something happening, and then you see damped harmonic motion. It's also nice to say something about resonance and anti-resonance. So when you have some vibrating system, and if external force drives another system to oscillate with the greater amplitude at specific frequency, it will cause some resonance in this resource. For instance, the simplest thing that you could think is, I don't know, dinging through glass, or for instance blowing to the bottle or something like this. It will influence some sound that will have connection to the tube itself. Since we have this through our speech all the time, so as we will see in the future, I would claim that there is a model that say that um, our vocal tract is actually a resonator that we use, and we change this resonator in order to produce different sound. So the idea that our vocal tract is resonator is really important. When we'll discuss nasal vowels, we'll also need something, this notion of anti-resonance. So this is also when you can find something like this. So when you there are different kind of rooms. In some rooms, echo will spread widely, and some rooms, when you have a lot of pillows and carpets, the sound will be absorbed. And this is because it can't move any further, and the absorption will be like on different scale. But it's also possible that there are some places when you can absorb only certain frequencies. And this will be a case when, for instance, you pronounce some, I don't know, nasals. You will see that some frequencies that we produce during the production of nasal consonants are actually absorbed. And this is because we open our nasal cavity and close our oral cavity. So we have something like ma. When you have ma, you actually reduce some sound and then you go for this. But we'll discuss it in more details when time came. And here will be a small. Yes, any questions? It wasn't? Okay. So let's move on. The next part about addition of waves. So imagine that we have two waves, and they are have similar features in amplitude. They have similar phase, and they have similar frequency. And as a result, we will get the wave that have the same frequency, the same phase, and the amplitude will be doubled. In order to do this, you simply need to add a value for each dot in one line to another. So for instance, here we have 1, add 1, you get 2. Here you have -1, add -1, you get -2. And so on and so on and so on. So this is the simple case. This could also be the case when you have waves that have different phases. So here frequencies is the same, phase is different. So they are actually 180 degrees difference in phase. So when we sum this up, we'll get something like this. So they are exclude each other. Here we have different in frequencies. So first wave is twice shorter than the second one. So, sorry, longer. So here you have one cycle, and here you have 2 cycles per the same, more or less for the same time. So frequency of the wave 2 is twice as frequency of wave 1. And as a result, you will get something complex, because when you, so see here, it's still really symmetric, but this is only for now, because real waves are weirdly non-symmetric. So here you see the first period, what's going on. So the first period, they are all, so two waves are increasing. So during this time, the first wave is increasing, and then it go down. And when they go down at the same direction for some time, it will go down here. But then you see these differences are stopped to changing. So here, for instance, you see that there are part when one wave is going up and another is going down, and that's why you have this simple, this small peak here and here, and then at the end they all go down. So that's why this peak is similar as this one. But the idea will be more or less the same. Just take one value from one wave and add a wave from another. The same idea will be with damped and forced waves, like here. So you see it's damped and forced, so there will be some mean value in the middle. And the last thing that I think it's important to say is beats. Beats is some change. So if you have two waves with two frequencies, but their frequencies too similar, but they are not the same. In that case, you will see something that called beats. In Russian, it's called биение. Have you ever heard such beats?
Is it like the beat in music?
Sorry?
Is it like the beat in music? Like, do you have a kind of bass or something like that?
If you mean drums, then no. Have you, anybody of you played piano?
Yes.
Cool. Congratulations. Do you know, have you ever tuned piano?
Not on my own.
Isn't that really hard to do on your own if you're not a professional? I thought.
I think that I'll find it for you. So here it is. I think, let's see this. So when you see something like this, you have this keyboard, and on this keyboard you have different notes. So one note is actually force some beat to the strings that are here. And if you look, I think here, you will see that they are all combined into blocks of string. And that's why you actually have not one string per note in most cases in piano, but two or three. So here you see block of three, and then there you see block of two. So if they are, so for lower notes, there will be less strings, but for upper it will be three. And here you have these connections, and when you tune like this, I actually can't remember, I don't know how to say called key in English, but anyhow, when you tune, you need to just rotate this and changing this strength of the length of the string. Afterwards, so when you have, when it's not tuned, you will have this beats, and probably you can hear it if We do like this piano and then how to
George, I think I have found some nice examples of this phenomenon in Wikipedia. So I don't know how to
yeah,
share the
we do.
sound. Yeah, but
Maybe they have the sound itself.
yes,
I think
it is beat acoustics.
I see bit music.
I have sent the links in the chat.
Oh, thank you. So if we go here, wow, why do we have it? We have it, because it merged. Okay, let's do like this. And probably they have here some examples. And I don't know whether you can hear it.
Yeah, we can.
Cool. Something like this. And probably they have different classification of, that's different frequency only. Okay, so this is something that you can find in music, or so it's really something that you can find in sounds production, except you have weird echo that do weird things with your mics. But in most cases, it won't influence. So you won't find it in acoustic research at all. But I think it's nice to know about those effects that can influence some sound waves. And I think after this, we'll got to the most important thing. This is called Fourier Transform. And Fourier Transform, it will be the main tool that we'll use through our acoustic analysis. So there are two of them. There actually will be duration analysis. So when we measure what is the duration of some units in of some chunks of sound that we analyze, and another, if we will be interested in acoustic features of some sound, we'll use Fourier transform. These Fourier transform are actually extract components of the complex wave. So we have complex wave like this, like over here. And then it will say that this wave consists of this wave 1 and wave 2, but also will say what are weights of this wave. So for instance, if you multiply wave 1 with 0.5 and multiply wave 2 with 0.25 and add them, you will get this wave. So Fourier transform will do it like, so starting with this complex wave, it will get you ingredients
But
from it.
why do we need to multiply it?
It's not important for now, I think, because they could be different influence. So for instance, in wave 1, for instance, will be after multiplication, the amplitude, the maximum amplitude of this wave 1 will be 0.5. and amplitude maximum of wave 2 will be 0.25. So this will be, so in order to get this wave with this amplitude values, we need to have those values for, so those multiplication for wave 1 and wave 2.
I'm just wondering, why do we need it?
Because it's, in most cases, we have only something on the top. So we have some complex sound, and then we want to extract some features of this sound.
It means that it will show us something more what can't be showed by the second and the third pictures. Yes?
The idea of Fourier transform that you see something like this on the top, and then after you said that it actually consists of two waves of those frequency, you can analyze those frequency. So this is important information. So wave 1 doesn't say nothing about the contents, its contents. It's just complex wave. Here we can see decomposition into two. So we represent one complex wave with the summation of simpler waves. So this is important.
Okay.
The important thing that those waves are simple. So if it's hard to imagine for now, and I'm not sure that we want to discuss some math behind this. It could be treated as a smoothie. So imagine that you have smoothie and you have one banana cut it in chunks. You have 1 cup of grapes. You have vanilla yogurt. You have 1.5 apple, and so on and so on. And then imagine that you have some person that you pour with this smoothie, and this person have a sip, and then after this person has a sip, this person can say what is the contents of this smoothie. It will be approximation, because in most cases person can't say how many apples were there and how many bananas, but it will definitely say the contents of this smoothie. So Fourier transform will actually do the same. So it will get you some simple waves. So it will decompose the complex wave into the simple waves, and it will also get those weights to those waves. So this with the weight 0.5, this with weight 0.25, and so on and so on. Is this clear? This analogy?
Yes.
Very clear.
I hope so. And here is the spectrogram. Spectrogram is the representation of this decomposition. We'll discuss it in more details, and maybe I will just show it today. But imagine that we have more or less the same wave that we've seen before. So here is some peak that it's actually really similar to this. So here on top, you see the oscillogram, and this is called oscillogram because of the word oscillation. So on the x-axis, you have time, and on y-axis, you have amplitude. And there are different types of spectrogram, but there is something that's called momentum spectrum. And you have this representation over here. And this kind of decomposition that we discussed before. So this is 300 hertz and 1000 hertz that are present here. So this is, so the peaks on this graph corresponds to those 300 hertz and 10,000 hertz. 10,000 hertz, probably 1000. No. Yeah, 1000. Or 1000. So here you have this sound pressure level, and this sound pressure level is actually kind of weights that we had here. So this plot over here represents that 300 hertz wave have a higher amplitude, and 1000 hertz wave have less amplitude. Is it clear so far? So this is the work of Fourier transform. I didn't show you how it was produced, but the result, it will be this. So I'm going through from this simple wave of oscillogram that I have on the left part, and here you see the spectrogram when you have frequencies on x-axis and some kind of weights on the y-axis. Okay.
I have a question about the spectrogram with two black stripes and one white stripe. So this is
we
like
didn't
very,
discuss.
very large.
So we didn't
We
discuss it
didn't.
yet.
Okay, yeah. Sorry.
For now, we are talking about this. I think it's possible to annotate about this one. Wow. Wow. No, I don't like it. Okay, it will be like this. So now we are talking about this from oscillogram to this momentum spectrum. So is it clear so far? I found.
Probably.
Okay. So the problem is for momentum spectrum that it accumulates all information about all sound. And it will work if we have fixed sound. So for instance, we have something like sounds that don't change any frequency during its production. But I think that you are aware that speech production is not like this. So during the speech production, you change frequencies a lot and sometimes even lose any information about frequencies itself. And you see some noises that give some information to us. So in order to have those, obtain the difference in frequencies, you need to have some time argument. And this could be done if we chunk this sound in oscillogram into smaller chunks. How to represent like this? Maybe it will work. So imagine that I have this chunk and I create a momentum spectrum like this on the right. Then I have next chunk like this. And the next chunk like this, and so on and so on and so on. So I split my sound into chunks. They are partially overlapped, and then you get those momentum frequencies for each rectangular that I drew. And after this, we can go through from this to this, because this spectrogram in the bottom is actually, whoa, I don't want you. Undo. This spectrogram on the bottom is actually combination of those momentum spectrum. how can you find it? So here we have from 0 to 03. So on the x-axis we have time. On the y-axis we have different frequencies. And on with color here, it's amplitude. So if you have darker values, then it's higher values. If you have brighter values, then it's low amplitude. So it looks like, imagine that I cut up this value and actually um, turn it to you and marked with the color the height of those peaks. And this is called uh, spectrogram. And this is not momentum spectrum, but time spectrum. So we discussed how to move from this to this and from this to this. Any questions?
Can we please discuss one more time the first step, how we move from the oscillogram to momentum spectrum?
Through Fourier transform.
Okay.
Sorry, it's short answer. But we can go I think I probably will send some link that will I think there is a video that I like that explains in some detail how Fourier transform works. But I think the previous year showed that nobody is happy when I try to explain it. So maybe for now it will be some magic tool that extracts frequencies from complex waves. And this smoothie analogy was exactly for this step, for Fourier transform step. Okay?
Okay.
So if I'm not mistaken, Ksenia was asking, why do we need to with this decomposition? The idea that after we decompose these complex waves into those frequencies, we can analyze frequency movements, and through this we can, for instance, say which vowel do we have in front of us, if it is a vowel. So this through the whole course, I think we will treat those information. So this transformation from simple wave to spectrogram and analyzing spectrum and trying to get information from the spectrum is one of the main goals of this course. We also need to discuss some small details of Fourier transform. As I said, we need to chunk our audio into smaller chunks in order to get this time spectrum or spectrogram. But there are different types of spectrum because as I discussed earlier, there is this window function. So I draw some rectangulars, colored rectangulars over the sound. And each rectangular is actually a window. It's it has a fixed size in seconds and fixed overlap with the previous window. And those two features are innate into the transformation from complex sounds to spectrum. But those window size could be different. And this is important feature. So it could be really small. then it won't capture much information what's happened in the sound. It could be so it could be really high, then it will just capture information about what's going on in sound, but there will be a problem that if it's huge, it will average everything around it. So with the huge window, we'll have the problem of that we won't exactly know what's going on in the in the moment of the time. So, for instance, increasing this kind of dichotomy that I would say that you either know more about here I think you either know more about frequencies in more details, or either you know about the time. It's impossible to know in exactly the way both with each Fourier transform. Uh, and those windows could be different, could be useful sometimes to change it, but in most cases, standard values will be okay. Is it clear what is window length and how it works?
Can you show what is a window one more time? I was.
Window is something like when we chop our sound into smaller pieces, like this. Here is the first piece, and so on and so on and so on. Then I change color.
And it's a window.
This is a window, and for each window, I calculate Fourier transform. This is important. That's why I have them.
Okay.
Okay, cool. So you have a lot of windows, then you have more information. But you know more about time, but Fourier transform is really bad in if you have a small chunk of audio, it's possible that full cycle won't be covered by window. If cycle is not covered by window, so it's not in the window, then it means that it won't understand that this is a cycle. What kind of cycle is it? So it will be wrongly estimate frequencies. You see? So that's why we don't have infinitely small windows in order to estimate something. Okay? And here are two examples of the same syllable car. Here is the oscillogram of this syllable, and here are different window length as I presented here. So it's 0.01, 0.05, 0.01, and 0.05. And here we see really small windows. So the spectrogram became like line wise. So you see there are a lot of different lines, and they are all probably informative, but the problem is that we can't see and conclude much from it about what's happening in time. Here we have 0.005, so it's a little bit greater. So the value is window is greater over here, and we see more details over here. So we see each cycle over here. And this cycle is represented, and here we have non-cyclic period. So that's why, so here when we have cyclic period, we see something happening every with some repetitions over here. That means that it's cyclic behavior, and here it's more or less random, as you see at the beginning. At this beginning, we have the small deviation from 0. That means that it probably is silence. And after this, something is started. So silence part represented more or less the same. So it's nothing over there. White, white, white. Here you see cycles, and here it's possible to see those cycles, but it's it's hard to understand what's going on over here. Here it's more clear. You see this part, it's not regular. You see this part is regular, and something. And this probably will be the standard window length that we'll use all the time. Imagine that we increased window length even further, and then we have not a window of size 0.005, but of size 0.05. In that case, we have more those lines that we've seen here. We actually have seen it here. So, for instance, imagine that could you see my mouse, aren't you? So this line.
Yeah, we can.
Cool. So here we have a line, and here we have a line, and here we have a line, and probably here we have a line. It's not clear, but more or less we have. And those lines are more like visible here, but here we have a problem that we lose information about those time chunks, about those cycles that we've seen here. And even these values over here, they are, since the window is really huge, it's averaged through greater chunks. So here we have not good time estimation for events. So here, instead of, so here we have something, here we have something, but here we have a blur, just blur information about what's going on. And this is what how window length influences spectrogram. Okay. Do you have any questions for now?
Как это сказать, в чем измеряется на первой картинке вот это вот 0,9797? Это герц или не герц?
I think
То есть по оси X это время, а по оси Y?
This is amplitude, and here the difference will be in decibels.
Okay, thank you.
So when we have oscillogram, the difference will be, so the difference that we see on the y-axis will be amplitude, and this is measured as decibels. Here, all others are frequencies in hertz and time in seconds. Okay, and it's important to say that it's the same syllable, and those are different representation. It's nice to have it here. Since Xenia, I think, Xenia asked about the correct version, and I still can't hear this question, but none of you asked me which is correct. And I would say that all of them correct, but everything depends on your goals. And this is the same answer that I already gave about the phonological theories at the previous lecture. I think that we have 3 slides or something.
May I ask a question? Can we go? Yeah, can we stay here? So what would we want to have the right windows for, like the right representations for?
So I think, so imagine that we create, so am I right that you asked why do we need this representation?
Yeah, and the one above.
And this one. Okay.
Yeah.
Okay, this is a solid question, I think. So first, imagine that I want to create a, I don't know, machine that will get vowels and get Forman values for this. I'm not actually interested in correct timing because I'm not interested in those cycles that are present here. What I'm interested actually to find anything that vowel-like and track those lines. And it could be easier to do with the window 0.05 because those also make less information. And since that, this will be increase speed of my machine. Why do you need window 0.1? I don't know. I've never used small windows. For me, they are mostly useless, and I think the same for machines. Yeah, so this will be my answer.
Thank you.
No, sorry, Anya. I think the one thing will be more precise here. Imagine that I'm interested in the first burst of the consonant. And if I want to represent them only with oscillogram, with the small window, it will be the most efficient. This line will be better representation than this one, because this is actually approximation. And this is a wider approximation than this one. So this line is easier to detect. And this corresponds to this. But this is something that I invented from my head because it's easier to do with oscillogram, I guess. But you still need to do something like trying to understand, try to distinguish these differences from differences that we have here in the silent part. Yeah, but this, yeah, this could be the answer to your question, I think. Okay? But
Yeah,
in
thanks.
the common life, but remember one thing, if you used to use spectrograms, remember that those things are just generalizations. Sorry. So, for instance, if you want to detect the beginning of the vowel or some time events, better use oscillograms because they are precise. Spectrograms are just approximation. If you are interested in timing, look at the oscillogram, not to the spectrogram.
And is it right that consonants are always like more dense, то есть более плотные in the spectrogram? I mean, ну что рисунок более плотный, когда у нас согласные?
I don't agree with this. I think we can do something like this. I don't know whether it will work or not. So if we cut the beginning, it will look like more or less like vowels. So yeah, but here we have it more intense. Maybe I think it's better to represent like this.
But if it's more,
Okay, sorry.
if it's dense, it means that more force is used in your production. Is it right?
No, I would say the opposite is right. So for vowels, you need more amplitude in most cases. R, r, r. it's kind of cheating. So I have a, and then r, and then a. So if you have it here, I wouldn't say that it's less dense or more dense. I think they have more or less the same. But with the trills, I think it's kind of cheating because it's actual vowel that disturbed by some beating. For this sound, it will be uvular, but it also could be something else. So, r, for instance, will have the same stuff. So you have vowel and during this vowel, you do tapping with your tongue.
And can you guess by the spectrogram where a consonant is used and where a vowel is represented?
Oh boy, I think in a couple of lectures you will need to guess a word looking onto the spectrograms. So it will be your task, and I hope that you will learn how to do it.
So it is possible.
Definitely. For some cases, actually, it's kind of stupid task because because uh, don't be silly because when you see a spectrogram, in most cases, there are two possible cases. First case is when you see it in your product window or some program when you see it. So it's easy to press play there and you will hear everything. So it's definitely not something, so this task is useless. Another task is when you see it in the published article and there is no any play button over there. But in most cases here it will be more or less ideal example of what's going on in this article. So uh, it so knowing what's going so seeing from the spectrum what kind of sounds was produced won't help you much there, I guess, in most cases. So it useless task, but it helped to learn how to work with spectrum.
But okay, let's look at the first picture. If you do not know anything, can you guess that it is car?
From the combination of the
Yes, only looking at the picture.
yes, from the combination of the picture on the oscillogram on the top and the spectrogram on the bottom, you can say a lot of things.
Okay.
And I think we have such tasks. You see, there are chapters in where is it? It's here. So there are probably maybe not this one. So here you have Russian words, but you need to decide. So here you have oscillogram and spectrogram, and you need to decide what is the order of words here. And it's possible to do with this task. It's easy task. And there are a lot of like this. And sometimes you don't even know. So here you expect that you look at this spectrum and oscillogram and spectrogram and guess what kind of animal probably you have here. So animal or bird. So it's solvable. Useless, actually, it's useless to as itself, but it's really nice to learn how to do it. Okay.
But
Yeah.
so are we supposed now to be able to do that, or we will learn something else to be able to do
I
that?
hope that we'll learn uh, So we will discuss. So I think several lectures from now will be about vowels, what kind of difference, how could we know vowels and what their difference between them. After this, we'll discuss some sonorants. After this, obstruents. That's all.
Mhm.
And after this, you'll have this lecture when you have a huge list of words and you need to guess the word.
Mhm.
So don't worry, don't worry. I don't expect you to do everything from now.
Okay.
Okay. The other thing that I want to say, it's a pity that I don't have links here, but I will update it in the future. It's possible to use other techniques, not only Fourier transform. Here, they have something like English word had. And probably on the top, they have this Zhao Atlas Marks distribution. And here they have simple Australogram. And here, the same story for the word right. So it's something that called reassigned spectrogram over here. So you see it's more precise. So even though here you have something like huge points for format rise. So here you see this line. Here it's more precise and more like dotted in frequencies and time. And here you have one huge blur. Here you have two lines separated from each other. So there are more techniques that to come in the future, I think, that will make this work easier. But I think for a trained phonetician, this will looks like fancy, but more or less the same. Yeah. So know that there are other procedures that will make it possible to move from complex sounds to spectrogram. Okay, and I think this is one of the last slides that I have. And this is source filter model of speech production. As you all have read in this chapter that we've sent you, there is some vocal cords in our throat, and they are vibrate. And during their vibration, they produce some frequencies that will a little bit decrease in amplitude, but will be multiply of some value. So it will be 100, 200, 300, 400, and something, and so on. Here we see glottal airflow. It's something that representation of so how we breathe. So we will breathe in, and then after this glottal airflow, air will pass through vocal cords, and they will oscillate and pass some air, then go back and close, then oscillate and get back, and so on and so on. So you will get something like a push, 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 stop, push, stop, push, stop, push, stop. And this is represented with this glottal airflow plot. And afterwards, this kind of this kind of wave come to our vocal tract. And vocal tract is actually a filter, so it works like a filter and resonates in some frequencies. So even if it doesn't work and doesn't change much, it will still resonate at some frequencies. So for instance, when you have it in most language, like sound, so this sound is actually a schwa type sound, is when actually you do nothing with your vocal cord and your vocal tract. And this kind of filter will work on those source frequencies that we that produce with the vocal cords. Since it's filter, it will have its own resonation filters for that we'll call formants in the future. But for now, it will be some bandwidth, some values of frequency in which values will be increased and all other values will be decreased. So here we choose 500, 1500, and 2500, and we will increase those values and decrease everything else. And when we apply these to our source spectrum that we see, the output spectrum will be filtered. So those peaks that we had here will decrease. So here you see first frequencies until 1000 will be all cutted and 1000 will be safe. Then again, everything will be cutted, and then in 1500 it will be saved. Again, it will be cutted, and 2500 it will be saved. Those frequencies of those values, frequencies of those values are taken from those 500, 1500, and so on frequencies of the filter. And this is a result of our vocal tract changes. So for instance, if you change position to E position, then your tongue will go up over here and will change those resonant frequencies such as first resonant frequency will be really low and the second resonant frequency will be really high, around 2000 hertz, and the low will be around 300 hertz. And this will influence on those harmonics also. And this kind of model that we will use all the time through our course. So the idea that we have some frequencies and then vocal tract somehow filter some frequencies out and some frequencies increased due to resonant effect. And this how we produce this that could be started for production of everything that is voiced. Is it more or less clear? No question. If you don't have any questions, this is something. Then I choose somebody. For instance, Maria Golubeva sounds reasonable. Masha, could you explain, for instance, those portions of intensity that we see in this Australogram? Do they correlate with those gaps that we see here or not? What do you think?
Sorry. I would say that, well, I'm not sure.
Sorry?
I'm not sure I can answer.
Okay. let's have somebody else. For instance, there are even two Alexander Smirnovs. Okay. Alexander, maybe you can answer. What do you think?
I think, as I understood, yes. So these gaps are poses, and so this I don't know how to say this. Pyramids are the pushes, and then these gaps are poses. So as I understand, the first picture in the high row corresponds to the first picture in the low row. So
okay.
And
do we have any other opinion?
I think they should not correlate.
Cool, Natalia, why?
Because frequency fluctuation that is observed in the lower right picture is conditioned by the configuration of the I don't know how it's called.
Tract.
Vocal tract, yes, but not by the fluctuation of I just forgot how they called.
Airflow.
Yeah, maybe airflow, we can say so.
I think that I agree with Natalia, because what we have here is actually we can analyze using axis titles. So here we have time axis. So it's something that's happening through time. And this surely correlates with the other time axis that we have over here. And this source spectrum have frequency, and there is no any time in this plot. So I hardly imagine that those gaps that we have here and those gaps that we have here are correlated, because as Natalia said, those gaps are influenced by vocal tract configuration itself. And these gaps are produced by airflow pushes. So the answer will be no, they are not correlated, because those pauses that we have here and gaps that we have on the upper plot is due to airflow pushes and vocal tract opening and closing. And here, all these ups and downs that we have here are correlates with the vocal tract configuration. It's not something that connected somehow to the upper plot.
Okay, and this 30, so from 1 to 30 on the axis y, it is not time. So there's frequency on axis x and on axis y. What is 30?
On 30,
it's decibels. Or
again, it's amplitude value. So we have it here.
Again, it's decibels and
yeah,
divided.
it's actually called sound pressure level, but let's assume that it's just amplitude values. It's a bit more complicated, but more or less with the same range. So it's correlated with amplitude.
So this arrow with I don't know, two pointed arrow corresponds only to the second picture in the high row and the second picture in the low row,
yes,
and not
yes,
to
yes.
to them all.
Yes, this is really important. Thank you for pointing it out. A vocal tract influence those frequencies that we have, filtering frequencies that we have in here. But vocal tract doesn't influence this, and vocal tract doesn't influence this. So we have something, and then we apply filter to it, and what kind of filter is depends on our vocal cord configuration. And this is the result after the application.
So this last picture is kind of distribution of frequencies of different amplitudes,
Uh,
or
I would say amplitudes of different frequencies.
okay, yes.
So those are amplitude of different frequencies. And remember that this plot is more or less the same plot as this. But we just applied some filter and filtered out some frequencies, and we obtained some peaks over here due to this filtering.
Now it's like I was confused. Time is definitely determined by airflow and vocal tract, but frequency also depends on the configuration of vocal tract, or it doesn't depend on it.
The idea, this initial frequencies are not connected at all to the vocal tract, because it's something that happened before vocal tract even interact with it. So this is the idea that these frequencies that we obtain if we cut off my head, but I will still breathing out some air, and my lungs, my vocal cords will vibrate, and you will have something like ah effect, but without my head, it won't be any ah, but it will be like I don't know. I can't do it because I can't cut my head for now. Definitely do in the future, but for now, sorry. So this representation is something if you cut my head and do measure everything over there in the glottis, and this what we obtain after the work of the head, let's say, of the vocal cord.
Mm-hmm.
Okay, and so the first picture in the high row and the first picture in the low row, they correspond to each other. So, but как это? Не дополняют друг друга,
I
да?
wouldn't say so.
Okay, so the first high picture, it is just it is a sound wave, yes. So it is, for example, a sound wave of sound A.
No, sorry, it's not.
Okay, so
it's not a sound wave. It could be, but it's said that it's going to airflow. So it's amount of amount of air that come from our lungs through our vocal cords.
And 400 and 200, it is like what? It is like the
I can't say you, but I'm afraid it's something like Pascal. So it's I'm afraid it's something like Pascal. So it's a measure of number of air go through.
And yes, no, то есть, so in the first millisecond, like this amount of air comes through vocal tract. Yes. In the second, this amount of air, in the third, this amount of air.
Yes.
Okay, and first low picture, it is okay. So so the first picture, what it is the frequency of this sound.
Yes, the frequency of the result sound, if we don't have any vocal tract, will be, so we have something like oscillating something like this, and imagine that we're just doing like this, and they are oscillates and produce something. And the idea that so the most frequent here will be the first value. So imagine that it will 100 hertz. And this will be a frequency of this oscillation. But there is a small story that we'll actually discuss in the future, that it's impossible to oscillate on using one frequency. In most cases, when you oscillate with the one frequency, you also oscillate on the same frequency, but for instance, twice. You know about this story about string. So if you have a long string and then you oscillate it, it will oscillate with the frequency of the length that corresponds to the length of this string, but it also oscillates with the frequency of the half of the string, 1/4, and so on and so on and so on. And this is why we have intensity or amplitude on all frequency are more or less the same, but just adjusting to the idea that it will be increasing on smaller, on higher frequencies. So the idea that we have here, imagine it could be written read as this. We have some harmonic motion, but it oscillates with some frequencies, and all frequencies are equal. But afterwards, we apply vocal tract filter, and it will cut off some frequencies and keep some others.
Okay, so I
I
have
think-
perhaps an additional.
Yep.
Sorry, I interrupted you.
Yeah. No. Go on.
I have perhaps an additional question. So if this source spectrum plot shows like frequency without vocal tract, so does it mean that this plot is similar for like everybody, for all people in the world? So because like vocal tracts, there are different, but this I don't know. But this frequency, maybe there are more or less same for everybody in the world, or this frequency is just for some particular unknown person.
I would say yes and no. Yes, but you need to adjust to the initial frequency, because it could be 100, but it also could be 200, 300, and so on. 300 will be too much, but anyhow, you can pick any number from 50, let's say, to 300. Okay. And another thing is the adjustment of other frequencies will be different for different people. So it's hard to measure this and to prove, because you need to cut a lot of heads. But this adjustment will be different for different people.
And could you say, for example, of what person this is the frequency of this source spectrum, for example? Because as I understood, we could sometimes say, so it is a children or it is an adult person, but could we look at this source spectrum, say what kind of person speaks like that? Oh no, it is.
I would say it's hard. I would say it's hard because in order to obtain this kind of thing, you need to have a mic inside human body in the upper, so right after your vocal cords. And if you record something there, you probably obtain something achievable like this. But remember that this is still a model. It's not like real data. So if you record it, you probably will get some differences, but there will be some particular there are also some particular things that we need to discuss in order to solve this problem. It's not so straightforward, I would say. I think we're out of time. So I proceed with, we far out of time. I think I will keep it, the summary like this, and we proceed next time with the prod. So probably it would be nice if you install prod for the future lecture. So here it's here it's page, and you can download it for Linux, Windows, or anything you want. Okay. So it's nice to have you. I hope that you liked our first lecture. And see you next time.
Thank you.
very much.
Thank you.
Thank you.
Bye.
George, excuse me, I have like one more small question. So these gaps, they corresponded to in the third plot in the low row. So they corresponded to what? So I understood about a third picture in the high row, but third picture in the low row. So
This
these
one.
gaps so I
they
don't
corresponds
see.
to something that we see here. So here, for instance, we have car, and this line that we have here is the first mountain. This is the second mountain, and this is the third mountain.
Are you trying to show us something? Because you're not showing.
I'm not showing. Like this?
No. In the very last slide.
So you
yeah,
asked
here.
about these peaks and these valleys.
Yes,
those peaks and
падение.
those values corresponds to the something that we see in vowels over here. So we see car, and here we have one line. This is the first peak, this is the second peak, and this is the third peak. And I think on the next lecture we'll talk about it in the more details. Okay?
Окей. То есть это просто три разные волны, да? То есть это первая частота, вторая частота, третья частота, и все они идут одновременно,
Конечно,
да?
это же у нас частоты написано.
Все. Единственное, что я вот не понимаю, что вот, то есть вы сказали про то, что по оси Y вот это то, что делится децибелы на герцы, но я так и не понял, не знаю, может быть, я забыл, как по-русски это называется. То есть вот это вот...
Эта штука?
Да,
Она там
вот
как-то очень
эта
мутно
штука.
называется, потому что вот здесь у нас амплитуды и децибелы, и все просто. А вот тут там какая-то логарифмическая шкала, которая там еще... На самом деле мы как-то не обсуждали, потому что если мы смотрим сюда, то у нас там они могут иметь только, ну, там, положительное, отрицательное значение, но как бы когда мы переходим вот сюда, у нас только какая-то одна шкала. И там есть какой-то переход, какая-то формула. Ну, в общем, это что-то типа... Это можно воспринимать как просто ну, как бы относительная сила, ну, вот относительная, ну да, интенсивность какой-то вот частоты. Относительно, в смысле, друг друга. В результате можем их сравнивать друг с другом.
Вроде это называется звуковое давление, то есть, не знаю, по крайней мере, перевод статьи Sound Pressure в Википедии на русский называется звуковое давление.
Ну, наверное, ну, вот я как-то... К сожалению, просто я, в смысле, вот такие графики мне почти не приходится использовать в жизни, и чаще всего мне приходится в жизни использовать вот такие, поэтому я, наверное, не знаю, как называется по-русски вот эта штука.
Хотя Sound Pressure Level. Может быть, это не то.
Ну, это хороший вопрос.
Да.
Я, наверное, попробую выяснить это к следующему разу.
Ладно.
А можно еще быстренько вопрос тогда?
Да.
Если мы вернемся к формуле волны, которая была в самом практически начале. Хотя нет, уже когда мы обсуждаем, вот да, вот здесь, когда мы складываем волны и чуть дальше, там у разных волн были разные коэффициенты. Я не очень понимаю, откуда берутся коэффициенты, когда у нас амплитуда, это же как раз громкость. И у нас... Что вообще значат эти коэффициенты? Как это?
Ну, вот здесь вот эти волны представлены как что-то равнозначное. У нас есть волна с амплитудой 1.
Да.
И значение амплитуды здесь 1, и здесь тоже 1. И мы принимаем вот это как за такую базовую штуку, и поэтому нам нужны коэффициенты. Потому что у финальной этой волны она даже сама не 1, а даже какая-то вот еще меньше. Ну, видимо, 0,75.
То есть разница будет только в амплитуде, то есть на первую и вторую. Окей, все, я поняла. Все, спасибо тогда.
Ну тогда всем до свидания.
Все, спасибо.